Kristen Atchison here, and this is our introduction to repeated measures ANOVA. So repeated measures ANOVA is using that same kind of technique that we had from independent measures ANOVA. We're just going to change a couple of things. So in independent measures ANOVA, they've got a bunch of different people in different groups. The samples may not be identical. So if these groups were different, what was responsible? Was it the treatment differences or was it the participant group differences? We don't know because we have individual difference in an independent measures one-way ANOVA, in an independent measures design. However, a repeated measures solves this problem by testing all the treatments using one sample of participants. So remember, a one-way independent measures ANOVA is used with a between subjects design, and between subjects designs have the major internal validity risk of individual differences. And we do our best to control those by random assignment, but they don't go away. Whereas repeated measures within subjects designs, we don't have individual difference. And so that solves that major risk of any participant group differences, any individual differences. And again, we'll use a repeated measures ANOVA to conduct a repeated measures or within subjects statistical test for that design. So when we carried out the independent groups ANOVA, we figured out our F ratio, and that ratio had the two kinds of variance. We had the between group variance, which had both a treatment effect, and it had our error in it. And our error in a between subjects design includes differences due to chance and individual difference. We also had within group variance was the other part of that ratio. And that again was our error term, and so it had differences due to chance and individual difference. Again, that's because it's an independent groups ANOVA. In that between subject design, individual difference is part of it. And so again, we had treatment effect and differences due to chance, over differences due to chance and individual differences, and these just cancel each other out. The difference of repeated measures ANOVA is that we don't have to worry about these individual differences. We don't have to worry about participant characteristics varying from person to person. We don't have to worry about those characteristics influencing the measures of the dependent variable. Repeated measures designs allow us to control for these effects of participant characteristics. It's eliminated from the numerator of the F ratio by the research design. Because we don't have between group variance due to individual difference, because it's within subjects design, it was never in the numerator. The problem is with the way that we calculate an ANOVA, we calculate it in to the denominator. So what we're going to have to do differently in a repeated measures ANOVA that we didn't have to do in an independent measures ANOVA is we're going to have to remove that individual difference from the denominator. We're going to have to quantify, figure out how much of that variance is due to individual difference, and we're going to have to pull it out. So again, it was never in the numerator because of the design itself, because of a within subject design, because of a repeated measures design. But with the way that we calculate an ANOVA, it gets calculated into that within groups variance. So we're going to have to quantify how much of that variance is due to individual difference and pull it out. So a repeated measures ANOVA hypotheses are the same that we've been dealing with in ANOVA. Again, null hypothesis testing, there is no difference among the treatment groups. And our alternative hypothesis is there's at least one or more differences among the treatment groups. Remember, we're not going to be able to write a mathematical a null hypothesis. We'll have to say, like we have here, at least one mean treatment differs from the other, or we can also write not the null, because again, there's a multiple different combinations of when the research hypothesis could be upheld, where the null hypothesis is not true. So again, the null hypothesis continues to be there are no differences. We just have the alternative hypothesis changes when we have these three or more groups. So the structure of the F ratio for repeated measures is very, very similar to that of independent measures. The only difference is there's no individual difference in it. We don't have this. Again, this has been removed from the numerator by the design itself because it was never there. And we're going to have to statistically or mathematically remove it from the denominator, okay? So again, the biggest change from the independent measures to the repeated measures ANOVA is the addition of a process to mathematically quantify individual difference and remove it from the denominator of the F ratio. So this is what changes, okay? So what we're going to find is that we're going to start out calculating this just like we would a one-way ANOVA. When we get done calculating our sums of squared between and our between groups and our sums of squared within groups, what we'll go on and do then is we'll move on to step 2. So we're going to add an additional step of sums of squared that we didn't have before. So again, in this F ratio for repeated measures, the numerator contains both those treatment effects, those systematic differences caused by the treatments, and any kind of random chance errors. The denominator includes what is, again, expected due to these unsystematic error. And this is what we have left over, this residual, after we remove the individual difference. You can see that a little bit better on this slide here graphically. We still have the additive relationship where between treatments plus within treatments equals total. But what we're going to do a little bit differently is we're going to divide up within treatments variance. We're going to say how much of this is caused by individual difference, and we're going to call that between subjects variance. And again, this is saying how are these people different? What are these individual differences within people? And the other piece of that, which will end up being the denominator in our F ratio, is our error variance. And this is what's left over after we remove that individual difference. This is the error that's due to these unsystematic factors that's due to chance. So step 1 of our repeated measures ANOVA looks exactly the same as our one-way ANOVA. So this looks absolutely identical. It's the exact same as one-way ANOVA. This will be the same. So everything that you've learned up to this point with one-way ANOVA, great. You're going to keep using it. We're going to start out calculating this as if it were an independent group's design. So step 1 will be absolutely identical. So again, the first stage is identical to the independent samples ANOVA. We're going to compute the sums of squared total. We're going to compute the sums of squared between treatments, and we're going to compute the sums of squared within treatments. What happens in stage 2, in this second stage, is this is where we figure out, well, how much individual difference is there in this sums of squared within treatments? We quantify that. And again, we call that sums of squared between subjects. We subtract this, we just remove it mathematically from sums of squared within treatments, and what we're left with is sums of squared error. Again, this is often called this is also called the residual. So these are these new formulas for sums of squared between subjects and sums of squared error. If you look at that sums of squared between subjects formula, it looks very similar to that sums of squared between treatments, and we'll talk about that in a second. So you'll calculate sums of squared between subjects, and you'll just literally subtract it from the total that you got for stage 1 for sums of squared within treatments. And that's how you get sums of squared error. Other textbooks will give you a formula to just calculate sums of squared error. This is how we do it in this class. Remember, there's no standardized notation for sums of square for ANOVA. And so again, this is how we'll be doing it in this class. So again, here's that comparison of the sums of squared between treatments formula and the sums of squared between subjects formula. Notice at the end of them, the g squared minus n is absolutely identical. The only thing that's different is that we have t's versus p's and little n versus k in the beginning. Okay, so in our sums of squared between subject, we said, well, what's the total for each group, right? And we divided that by the number of people in that group. Okay, so that's what we did for that sums of squared between treatments. And we're going to do the exact same thing, the number of scores in each group. We're going to do the same thing in repeated measures ANOVA. And so we went down, right? We went down through a column, we added up a column, we got a total for that column, and we divided it by the number of scores that went into that column. We're doing the exact same thing in between subjects, except here we're going to be adding up kind of a row. We're going to be adding up every score from that person and dividing it by the number of conditions, the number of, or K, which is the number of scores that went into that total P. We call it a P for a person total. So that's what that P is standing for. So we're doing the exact same thing we did in between treatments, except in between treatments, we look to see how the groups are different. And in between subjects, we're looking to see how the subjects are different, how the people are different. So again, that we can quantify individual difference. Here are degrees of freedom formulas. Again, degrees of freedom total within treatments and between treatments are absolutely the same. Between subjects is a new formula. And again, we'll just take the number of people minus 1. And then degrees of freedom error is new as well, but it's still additive the way that sums of square was. So we'll just take within treatments degrees of freedom, subtract out between subjects degrees of freedom, and that leaves us with degrees of freedom error. The way mean square formulas work is it's kind of a matching game. So you're going to match up the sums of squared with its degrees of freedom. So sums of squared between treatments goes with degrees of freedom between treatments, and that gives us mean square between treatments. Sums of squared error goes with degrees of freedom error, and that gives us mean squared error. Remember, this sums of squared error is that residual, is that variance that's left over after the individual difference is removed. And that's the mean squared that's going into our F formula. So our F ratio ends up being mean squared between treatments over mean squared error, and that gives us our F. Again, what that is our treatment effects plus our unsystematic differences, those chance differences. And remember, there was never any individual difference in the numerator, right? There was never any individual difference in the top because of the design of the study. And then the bottom, our denominator, is just that unsystematic differences. Again, it doesn't have individual difference. That's been removed. We statistically removed that. We quantified it with our sums of squared between subjects formula. We figured out how much variance was due to individual differences, and we pulled that out. Okay, so this is that concludes the introduction for how to do this. There's another video that I recommend you watch that walks us through a practice problem. So I encourage you to do that, and I'll see you in class.